Okay, I wanted to talk about how modern LCD displays work on cell phones or on projectors. It's based on the concept that everything you see is based on liquid crystals and polarized light. So when you pass light through an initial polarizing filter that's horizontally polarized, only the photons with that type of polarization, that directionality of polarization, pass through. And if you let that light pass through a second polarizing filter, as long as that filter has the same orientation as the first filter, that means that you can hear the, you can see the light passing through. But after that first polarizing filter, if you look over here on the right, if you allow it to pass or try to pass through a polarizing filter that's turned 90 degrees, orthogonal to the first filter, no light will pass through. And that's the basis of liquid crystal displays or LCD screens or LCD projectors. So let me just double check on the Q&As here to see if someone's asked if I pass on my annotated notes. Yes, I'll do that. Okay, so let's go ahead and talk a little bit more about this. So when you look at an LCD-based phone, way deep underneath that phone, there is an illuminated screen that is projecting all white. And what's happening is that the phone, each little pixel, is blocking one of three different colors of light. It's either blocking red light, or it's blocking green light, or it's blocking blue light. So everywhere you look at the phone that's got a cyan color, it's allowing green and blue light to make it through this liquid crystal display. If you look at areas that are 100% white, it's allowing red, green, and blue to pass through on that one pixel. And those pixels are so close together, they get mixed together and you can't tell the difference between white. And then finally, if the color magenta shows through, well, that's red and blue. That means that the green light is not allowed to pass through. Something is blocking it. And it's this idea of polarization. Something's blocking it, and so only the red and the blue photons are allowed to go through. And really the most amazing thing to me about an about a LCD display is the black regions, where none of the light that's behind your screen is allowed to pass through that cell phone. Your cell phone is still producing all of that white light, just none of it is allowed to pass through. So let's go ahead and talk about what's allowing the light to pass through or not pass through. And this is liquid crystal in that thin film of display. If I come back, this sheet that's overlaying on top of this white projector on your phone is based on organic molecules. Sometime 100 years ago, scientists realized, I don't know if it was chemists or physicists, realized that long molecules, long kind of flat, or not perfectly flat molecules, but longer molecules have this ability to control whether light can pass through or be blocked. They can polarize light, just like a polarizing filter. And what they later found was that they could control the direction of those molecules using electricity. And that's the basis for an LCD display. The molecules have become more advanced. You can see in the 1970s, we used to have these handheld calculators that had these tiny LCD displays, just one color. It was either black or grayish green. And now in the 2000s, these molecules have fluorine substituents. They all have aromatic rings. So you have to know how to do electrophilic aromatic substitution to assemble molecules like this. And they put them in those thin films, and they control whether light is polarized in this direction or that direction, and they can switch that back and forth very fast using electrical signals on any pixel of your screen. It's kind of amazing. And over here on the right side, I'm showing you a table from a recent research publication where people are trying to develop even better liquid crystal organic molecules. It's all organic chemistry that's making your LCD display work. I hope we have a chance to talk about the OLED displays where it's actually the molecule itself that's emitting the light. Super fantastic and super interesting. All right, here's us for today. Let me see if I can get this autofocus on here. This may look kind of like a page I showed you before, but it's a little bit different. I showed you a slide like this before in order to distinguish what kinds of substituents, if they're attached, if one of these substituents, just one of these, is on your aromatic ring, does it stop Friedel-Crafts reactions from working? And I told you that all of the meta-directors from carbonyls down on down, you can't do Friedel-Crafts reactions. And I told you that amines were also particular for shutting down reactions catalyzed by aluminum trichloride. Friedel-Crafts reactions just have so many exceptions. It's hard to remember all those exceptions. That's really the work for our chapter on electrophilic aromatic substitution. Okay, so what is this slide about? This isn't really about the limitations of Friedel-Crafts. It's kind of the culmination of everything that the chapter on electrophilic aromatic substitution is all about. Because what it shows you is that if you have two different substituents on your benzene ring, now it's a little bit harder to decide what the regiochemistry of the third substitution reaction is going to be. So if we now, for a third, add a third substituent by substituting one of these remaining hydrogens, how do we decide what will be the regiochemistry in the addition of the third reaction? So if I do a bromination reaction on this phenol, you may recall that with phenols, you don't have to add FeBr3. You shouldn't be adding that when you brominate phenols, OHs. Because they're so activated. Or if we do a sulfonation reaction on this benzoic acid derivative at the bottom, where will that third substituent go? Where will that sulfonic acid residue go? And so in order to decide that, you absolutely need to memorize this ranking in order from top to bottom. You have to memorize this ranking. There's no way around it in order to answer these types of questions. I promise you, I'll be asking these types of questions. Professor King will be asking these types of questions. Professor Van der Waal, everybody who teaches organic chemistry asks these kinds of questions where you have to understand the relative order of activation of these substituents. And the simple rule that we have for deciding where will the bromine go, the two ortho positions, ortho to the hydroxy, are equivalent, and the two meta positions are equivalent. So will you go ortho to the hydroxy or meta to the hydroxy? Will you go ortho to the methyl, or meta to the methyl? And the rule is the strongest activating group in the starting material, there's only two groups here, controls the regiochemistry. So when we put this bromine on here and we have to decide where does that bromine go, we have to decide which of these two groups is a stronger activator or is higher in this list. And when I say stronger activator, I also mean least strong deactivator. So strongest activator is kind of the same as saying the least strong deactivator. So the higher in this list, the stronger the activator will be. So for example, here, I've got an alkyl group and I've got a hydroxy group. And I come over here to my little list and it looks like OR or OH is higher than alkyl. So that means the hydroxy group is going to control the regiochemistry. And hydroxy groups are OrthoPara directors. So this is going to direct the bromine to add either para, but that's blocked, or ortho. So it's going to add ortho. So the product of this reaction is going to have a substituent, a new bromine substituent at the ortho position to the hydroxy group. It's the hydroxy group that controls the regiochemistry of that third substitution reaction. Okay, let's come down over here and apply that same rule where I have a methyl group, which is an alkyl group, and a carboxylic acid. It's a carbonyl derivative. So my rule is the strongest activating group controls the regiochemistry. So I have an alkyl group, and then down over here, lower down, I have a carbonyl. Alkyl groups are stronger activators, and they're OrthoPara directors. If I had two of these groups down here, one of the two meta directors would control. You just have to know which one is the highest in this ranking. So here, the alkyl group, the methyl group is the stronger activator, and so the sulfonic acid is going to be directed orthopara by alkyl because it's the strongest activator. And these two positions down at the next to the ortho to the methyl group are indistinguishable, so it doesn't matter whether I put it on the right-hand side or the left-hand side. So let me go ahead and put, just because I have room, I'll put the sulfonic acid over here. Okay, that's that simple rule, but you have to memorize this ranking. You've got to memorize these, and you've got to know, which of these are meta directors, meta, 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 and all these ones up above here are orthopara, etc. I'm not going to write all that in. Okay, memorize that, and then go work a bunch of problems in the book and in Sapling, and in our discussion sections. I'm sure we're talking about it this week, starting today in discussion section, using that rule. Okay, when we've got let's talk about another kind of a simpler rule, but it's maybe a little bit obscure, about regiochemistry. So this is another slide about regiochemistry and how to decide where the third substituent is going to add if you've already got two substituents on a benzene ring. And let me go ahead and try to, I feel like I'm not sure if I can see maybe that's too big. I'm not sure if you guys want to see my face that big on this, on the screen. Okay, so when you've got two substituents on a benzene ring, right, let's take a look. The methyl group on top is an OrthoPara director, so it would direct here, here, and on the bottom. And then this methyl group over here on the side will direct ortho and para. And so to the same positions, but will you go in between the two methyls, or will you go on the other side of the methyls? And there's a simple rule, is don't substitute in between meta-substituents. Because if all else is equal, it's better to substitute here than in between these other two. So you get one product out of this reaction. You only get the substitution that's para to one of these groups, to the group on top. It's para to the group on top. The substitution has occurred para to this group, and it has occurred ortho to this one. But it did not occur ortho to both of these, because it's just faster to substitute down at the bottom. And over here is an equivalent position. What if you had ethyl and methyl? Well, probably you'd get a mixture of, you know, some next to the ethyl and some next to the methyl. But I would never ask that question, because that, right, I don't like asking questions where you get a one-to-one mixture of things. Okay, so just kind of a simple idea. You don't get any of the product where you substitute in between. I'll just put in here, I'll just write no. That's not formed. You know, that would still follow your OrthoPara rule, but now we've got this extra little rule that we have to remember in addition to all the other stuff you've got to keep in your mind. Now, when you add alkyl groups to benzene rings, alkyl groups are kind of boring. Right? It's not all that great to have just a simple alkyl group attached to your benzene ring. Sometimes you want to do things with the substituents that you add to benzene rings. And so we're going to talk about some reactions you can do with the substituents that you put onto benzene rings, with alkyl groups, with carbonyl groups, with nitro groups. Let's go ahead and talk about one of the first of these, and that is how to take an alkyl group attached to a benzene ring and convert it into something interesting. And we're going to borrow a reaction that we learned back in chapter 15 in the 5th edition of the Smith textbook. I don't remember, it's the chapter on radicals. And back in the chapter on radicals, you learned this reaction where if you take an alkene that has allylic hydrogens, let me draw those two allylic hydrogens, you can abstract one of those allylic hydrogens in order to make an allyl radical. And let me go ahead and draw that allyl radical. Here's the allyl. I like to draw all the H's attached to things that have an allyl radical. But there's another resonance structure we can draw for that allyl radical that looks like this. And let me draw all the H's on this, and that other H is still over here. So when you pull this H off, you get this resonance stabilized allyl radical. And when it gets trapped by bromine, you can trap at either position. And so you generate these horrific mixtures. No organic chemist likes to get mixtures of products. This is why you haven't really used this much since chapter 15. Why did they bother teaching you allylic bromination? It's so useless because it gives these mixtures. But we're going to take that same reaction mixture, N-bromo-6-cinnamide. There's actually a simpler mixture that we can use, or the same type of reaction. We're going to take that same type of reaction and apply it to benzylic substrates, and for the first time, that's going to be useful. And the reason is that the way this reaction works is when you have benzylic hydrogens, you can substitute one of those using either the same or even more types of conditions than you used back in the chapter on radicals. And the rule is that if you have benzylic hydrogens and you treat those with N-bromo-6-cinnamide, with light or with heat or with peroxides, well, that's really frustrating to me that they give you 3 sets of conditions: light, heat, or peroxides, and they don't tell you which one is better. That's crazy. Why don't they just tell you one set of conditions? I only wrote one, but if you wanted, you could write high temperature, delta, or you could write peroxides. Oftentimes they use more than one combination of those, like peroxides and light. When you do that reaction, you substitute one of these benzene rings, or sorry, one of these benzylic hydrogens for, excuse me, I got to just do a little changing here. You substitute one of these benzylic hydrogens for a bromine atom, and that's useful because that's now a leaving group. If you wanted, you could do SN1 chemistry if you make the conditions polar enough to generate a benzylic carbocation. If you wanted, you could do SN2 chemistry if you use a nucleophile that's so strong it doesn't wait around for it to form a carbocation. But what we're going to find out in chapter 20 is that you can convert carbon-halogen bonds into super powerful nucleophiles. That's what's really useful about that. So here's some of the other conditions you could use for that. Notice you could use Br2 for benzylic bromination. You can't use Br2 for allylic bromination because that would add Br2 across the double bond. So, so any of these three sets of conditions, I'm just kind of writing one set here. Now notice, because we generate a new stereogenic center, any reaction where you generate a new stereogenic center, you'll also get the other stereoisomer because you can't choose whether the bromine adds to the top or the bottom face, so you also get the mirror image there, and you have to remember that. Let me just give you another example, right? Just to make it a little, reinforce it a little more. You could have a halogen on there. Doesn't stop that from working. We could have other substituents on here, like a carbonyl, doesn't stop. As long as there's those benzylic hydrogens, you'll get that benzylic bromination. And again, you could use Br2 in heat or one of these other combinations of reagents. I don't know why I drew the opposite resonance structure of the benzene ring. I wasn't trying to imply anything. And then, of course, there's two hydrogens here. Let me draw them in. And one of them will get substituted. I'll draw in the top one. And there's our bromine atom. And I'll write plus E, because if you generate a new stereogenic center, I expect you to know that you generate both stereoisomers at that stereogenic center. In this case, it would be the mirror image of that molecule. Okay, so it's really useful and interesting to put leaving groups at benzylic positions. And you don't have to worry about this stupid regiochemistry problem that made allylic bromination completely worthless to synthetic organic chemists. And probably the more useful thing is that we'll teach you in chapter 20 how to convert carbon-bromine bonds into super nucleophilic bonds. All right, let's take a look at another reaction of benzene side chain or benzene functional groups that's useful, that you can find potentially useful. And I'm going to give you two different recipes for burning a carbonyl all the way down to a CH2 group. And it's a little bit weird about how that is potentially useful to you. Okay, so here's the first. We're giving you two recipes, and generally I don't like it when they give you two recipes for something, because why not just give you one recipe instead of giving you all this extra stuff to learn? The first recipe for this reduction of carbonyls is called a Wolff-Kishner reduction, and you don't need to know that. I don't care if you know what it's called, but I expect you to know the ingredients. It's hydrazine. There's a nitrogen-nitrogen bond in hydrazine, H2N bonded to NH2. In base, sodium hydroxide, and you boil the heck out of this thing. It doesn't work at room temperature. If you forget the delta, it's wrong. So you have to include the fact that there's heat there. And when you do those conditions, the carbonyl gets converted to a CH2 group. I'm not going to draw the H's on there, but there's two H's there. So where you had a carbonyl before, now you've added two H's. And the reason why this is important is you may recall you can't do this directly through a Friedel-Crafts reaction. Because if you try to do this transformation directly through a Friedel-Crafts by making a primary carbocation, primary carbocations rearrange to give either hydride shifts to give tertiary carbocations. You can't do Friedel-Crafts with primary carbocations that are capable of undergoing rearrangements. And I'm just going to say, no, you can't do that. So if you wanted to put this group here with a CH2, don't try to do a one-step Friedel-Crafts. You have to do a Friedel-Crafts acylation, and then in a second step, you reduce down. So let me try to draw the carbocation. You couldn't do that with this carbocation of Friedel-Crafts directly, because if you tried to, this hydride would migrate over and you wouldn't get this product directly. But you could do a Friedel-Crafts acylation and then use this reduction. Now there's a second set of reducing conditions that uses zinc mercury amalgam. What is that? This symbolism is so weird. It shouldn't mean anything to you. Here's what it means to me. When I see some metal and then I see parentheses, another metal, usually mercury, it means they took zinc powder and they mixed in a little bit of mercury to coat the little mercury powders, little zinc powders with mercury. And it just creates a super reactive surface. So I'm going to say zinc mercury amalgam, but you don't even need to know what it's called. You just need to know use this specially mercury activated form of zinc powder, zinc parentheses mercury, and then hydrochloric acid, very aggressive conditions, and you're boiling it, just like the one above where you're boiling in strong, powerful base, the one below, you're boiling in strong, powerful acid. And it leads to exactly the same overall transformation as this Wolff-Kishner reduction. This is called a Clemmensen reduction if you care, but there's no reason for you to care. And it converts a carbonyl directly down to a CH2 group. This reaction doesn't have to be on aryl ketones. You could have other groups there, but usually you're not using it in most cases because there's usually easier ways to make these things if it's not a benzene ring next door. Okay, why would you choose one over the other? If you had a base-sensitive functional group, maybe something that was sensitive to E2 elimination, don't use these top conditions. Because if you've got some other functional group on your molecule that's sensitive to E2 elimination, then you're gonna have to worry about that. Where this would be valuable is just suppose that you had a substrate where you were worried about an SN1 reaction. Like let's suppose you had an acid-sensitive functional group on there. Don't use the bottom conditions, right? That's sensitive to acid. If you put this kind of tertiary benzylic alcohol on a substrate, don't use the bottom conditions. That tertiary alcohol is acid-sensitive. Tertiary ROH, acid-sensitive. So use the basic conditions for that. And then likewise, if you had some substrate over here that was sensitive to base, then I would not be using some conditions like what would be sensitive to base. Maybe this. If you put that in sodium hydroxide, it would do an E2 elimination. So don't try to do these top conditions if you have something that's sensitive to base. So this whole, I'll just try to put this here. That's base sensitive. So that's why you would choose the bottom conditions. I'll just write E2, base sensitive. So that's why I'm giving you two different recipes. Oftentimes I'm frustrated if the book gives you two different recipes and doesn't explain why you would do one. Now, you're going to panic later on in this quarter and you're going to think, oh, Van Vranken said that every carbonyl in the world can be burned down to a CH2 group using either these Wolff-Kishner or Clemmensen reduction conditions. That's not true. There's a huge limitation to this reaction. Every time that you have an ester where there's an oxygen next to the carbonyl, you cannot use either of those two conditions. It won't work. You also cannot do, and I'll also put neither, could you do amides? You can't do amides to reduce using these two conditions. Now we will tell you a different secret reagent coming up that can reduce this down to a CH2. Neither can you, I'll write neither can you. Neither can you use those two conditions above to reduce this down to a CH2. It's only with ketones or aldehydes, but not when there's an oxygen next door to the carbonyl, not when there's a nitrogen next door to the carbonyl. This is only for ketones and aldehydes that you can use these two conditions. Okay, I feel like, I'm not sure if that was worth all that discussion, but they just seem to love to work this side reaction of primary carbocations in the book and then force you to find clever ways around that. And it's not really what organic chemists spend their time worrying about nowadays. Okay, so I gave you this example where, right, you couldn't do a simple Friedel-Crafts reaction on this, because if you try to do a Friedel-Crafts reaction on this, right, this combination of aluminum trichloride, it's not really the benzene ring, but when the aluminum trichloride pulls off, when the aluminum trichloride pulls off that chlorine atom, this rearranges so quickly, faster than any benzene ring can attack, faster. It's instantly rearranges to give you this tertiary carbocation. And the only product that you get of this, after the benzene ring attacks and you deprotonate the uranium ion, the only product that you get out of this is the Friedel-Crafts substitution reaction, where you've added a T-butyl carbocation. Even though you started with what's called an isobutyl chloride, an isobutyl substrate, you only get the T-butyl substituted. And so this is where you would use that two-step process I showed you on the last slide. Step one, sometimes the book enumerates things with brackets. I'll just put it over here. Sometimes like this, one, and then they put step two. So that's the way the book oftentimes I like to enumerate things. If I'm not isolating the intermediates, I use lowercase Roman numerals. And if I'm claiming that I expect you to isolate the intermediates, I use Arabic numerals here. You know, any one of these is fine as long as you enumerate the steps to make it clear you're not dumping in everything at once. So in other words, if we put in our recipe for Friedel-Crafts acylation, this acyl chloride and aluminum trichloride, and then in step two, we put our next conditions. We put in, we could do either the base or the acid here. I'll use those basic conditions for the Wolff-Kishner reduction. Hydrazine, sodium hydroxide, and heat. And you just plain have to memorize those three parts of this recipe. Okay, this two-step procedure will generate this isobutyl substituted benzene ring. And you have to know that sequence. If you want a CH2 group next to a benzene ring, you're probably not going to be able to easily get there with a Friedel-Crafts alkylation, because you're always worried about, oh, is there some group on there that can do that 1-2 shift, that 1-2 migration? All right, boy, all that work around Friedel-Crafts, all the complexity with Friedel-Crafts. What a pain, what a pain. Okay, let's talk about carbon-nitrogen bonds on benzene rings. I think I said before that even though it's easy to nitrate a benzene ring, nobody really wants a nitro group on their benzene ring. You know, most of the organic chemistry that's going on is happening to make powerful pharmaceuticals, super potent pharmaceutical drugs. And it turns out that nitro groups on benzene rings generally tend to cause liver toxicity problems. So, but you'll find lots of groups with drugs with amino groups on benzene rings or substituted nitrogen atoms. And there's a simple way to transform these kinds of nitro groups into amino groups. And that recipe is hydrogenation. So the same conditions that you used to hydrogenate alkenes down to alkanes, that's hydrogen gas and catalytic palladium on carbon. The palladium on carbon, it's just carbon powder, and they've coated the surfaces of the carbon with metallic palladium, but it looks just like charcoal powder when you buy it in the lab, but it's expensive. Not that expensive, whatever, simple conditions. Hydrogen, H2, palladium dash carbon, and what a great reaction. If you ever go into the lab and you want to run a reaction that will make you feel good because it'll work every time, that's a reaction that'll work. There's one slight exception to this reaction, is that not only does it reduce amino groups down, but it unfortunately hydrogenates alkenes. And sometimes you just want to reduce the nitro group and not hydrogenate the alkene. Moreover, if you have a carbon-bromine bond or a carbon-chlorine bond or a carbon-iodine bond on your benzene ring, these conditions also cleave that bond. So you can't use hydrogen and palladium on carbon in the rare case where you happen to have a halogen on your benzene ring. We need a second way to reduce down benzene rings in that case. So, and the conditions that we use are these two-step conditions, and I'm going to use a lowercase Roman numeral just to clearly indicate you can't dump everything together at the same time. The first part of this recipe is you use tin metal powder. So just tin powder. We can buy bottles of tin powder from chemical suppliers. And this is supposed to be HCl. Sorry about that. That's the worst looking HCl I've ever seen drawn, but that's HCl. But now I'm worried you're not going to remember it because I drew it really poorly. So let me do a good job of drawing that. HCl, tin and hydrochloric acid, tin powder. Dump in some tin powder, dump in some aqueous hydrochloric acid, and it'll reduce down that nitro group into an ammonium. But under the acidic conditions, HCl, if this is stirring around in hydrochloric acid, this is going to be protonated. The product would be an ammonium salt. And so you have to write down as step 2, some sort of a base. The easy one is aqueous sodium hydroxide to deprotonate it to give you back the free amine. Because if you don't write step 2 here, you'll end up with an NH3 plus Cl minus salt. And that's not what I drew as the product here. And you can't have the sodium hydroxide there in the presence of the HCl. If you don't enumerate those steps, it's wrong because the reaction won't work if you've dumped sodium hydroxide into your tin reaction. You have to wait until this top reaction is done, and then you simply use a separatory funnel to mix the mixture with sodium hydroxide. Okay, so again, the tin reduction of nitro groups doesn't cleave carbon-bromine bonds or carbon-chlorine bonds, and that's why they don't mention it in the book, but that's why you need to know that second recipe. But in almost all the cases, you're going to use hydrogen and palladium on carbon. Now this chapter they've shown you a bunch of reactions and how to put a substituent on a benzene ring using one of those 5 recipes, how to put a second substituent on the benzene ring and know whether the first group was an ortho, para, or meta director, and then using those rules I gave you. If you have 2 substituent, the more activating substituent, the higher substituent in that ranking list controls the regiochemistry when you add the 3rd substituent. So the book just loves making you remember all those and strategize on how you're going to synthesize molecules. So here's an example of a type of synthesis question that you would be confronted with either on exams or in discussion sections or in sapling problem sets. In any class, this is the kind of question that they like to ask. The example would be, if you start with benzene, how do you synthesize this molecule over here using the correct reagents and the correct end conditions and the correct sequence of reactions? So what reagents and conditions and in what sequence would you put them together in order to achieve this? Now, sometimes the best way is to work forward. Sometimes the best way is to work backward. And oftentimes when I'm approaching a synthetic strategy problem, I don't know whether I should start working backwards or start working forwards. I'll give you an example of how to think about that. So, one way to think about that would be really to ask, if I had a nitro group on a benzene ring, is there some way, if you try to work backwards, is there any way to put that alkyl group on there if you have a nitro group already on there? And the answer is no. The only way to make a carbon-carbon bond on that benzene ring is to do a Friedel-Crafts reaction. And remember those exceptions with the Friedel-Crafts? You cannot do Friedel-Crafts reactions on benzene rings if it has a meta-director as the substituent on the benzene ring. So this is just plain out. You're never going to be able to first nitrate a benzene ring and then do this, because the rule is no Friedel-Crafts if there's a meta-director. It's too deactivated. So let's just forget trying to nitrate the benzene ring and then put on an alkyl group, because it doesn't matter whether you try to do Friedel-Crafts acylation, Friedel-Crafts alkylation, that's just not going to work. Probably we better make the carbon-carbon bond first. But we can't make a carbon-carbon bond by doing a direct alkylation, right? If we try to do this and then aluminum trichloride, we're not going to get a propyl group on the benzene ring because the primary carbocation would rearrange. So we're not going to be able to do this directly if that's what we wanted to do. So I'm just going to say, no, that's not going to work because of hydride migration, H shifts. The primary in primary carbocations. So you can't directly put a primary alkane onto a benzene ring. Remember the two-step thing I showed you before? If you want to put a propyl chain on a benzene ring, we have to do a lot of work to make that happen. What we need to do is we need to take an acyl chloride and do a Friedel-Crafts acylation reaction. Here's something with 3 carbons. And if we do that with aluminum trichloride, we'll get a high yield of ethyl, phenylethyl, ketone. And now we can reduce this down using one of those 2 sets of secret conditions that I showed you before. It's kind of arbitrary. I could do the hydrazine base and heat reaction, but in this case, I'm going to show the zinc-mercury amalgam, the Clemmensen reduction, zinc-mercury amalgam, hydrochloric acid, and heat. And that'll take this carbonyl group all the way down to a CH2 group. Now I've got the propyl group that I wanted. There we go. Now it's a CH2 group. And now we can talk about nitration reactions. Now, alkyl groups are ortho-para directors. And anytime you need an ortho derivative or a para derivative, in my class and in every Chem 51C section, they allow you, actually I shouldn't even draw it here, they allow you to pretend that you could either get the ortho or the para efficiently. So you'll get 2 products after you do a nitration. You have to memorize those nitration conditions. What is it? The conditions for nitration were nitric acid. And what's the other thing that you need here? You need a strong acid. The other thing you need is sulfuric acid. There you go. So I could put the nitro group at either of these 2 positions or at the para position. I'm just going to write it down here, O2N. But the other product that you get is nitrated at the ortho position. And you typically get about a 1-to-1 mixture. And I'm just going to write the word separate. You either have to crystallize them apart or do silica gel chromatography to separate them. They move through a column of silica gel at different rates. That's how we separate most compounds. And so we will allow you to pretend that this is a chemical step, is separation of para and ortho. Anytime you want the para, just write the word separate, and we'll understand that you were able to separate out the para product. Or just put separate from on this side, and we'll assume that you can treat that as a chemical step and easily separate ortho products if you want them from the para products. So see all of the exceptions you have to memorize here in order to do multi-step synthesis to synthesize substituted benzene rings. Again, the textbook loves that, to ask you about that stuff, make you memorize the exceptions. I'm kind of going along with that. I will ask you to strategize synthesis. Maybe not so much in this chapter, but a lot coming up in the coming chapters.